Hello everyone. From this module, we will start studying about mass spectrometry. In short, we call it as MS. So far, in the earlier 15 or 16 modules, we have concentrated mainly on other spectroscopic techniques, starting from 1H NMR, C13 NMR, heteronucleus NMR, and as well as 2D NMR, that is two-dimensional NMR with respect to COSI and NOSI. And this is the extension of those spectroscopic techniques, and this is the last spectroscopic technique that we have got in our syllabus, that is mass spectrometry. This name itself sounds somewhat different because of the reason that earlier we used to call NMR spectroscopy, but here we are calling it as spectrometry, because in this case there will be no absorption of characteristic electromagnetic radiations. That means to say, when you say 1H NMR, C13 NMR, IR, UV, or other spectroscopic techniques, so when you place the sample in the instrument and when you pass the radio frequency radiations, those molecules or sample of interest will absorb the energy, and hence they are called spectroscopic techniques because it involves absorption of radiations. Here in this case, mass spectrometry, there will be no absorption of characteristic electromagnetic radiation, and hence the name spectroscopy is not used, but in various places, including some textbooks, you will see that it is called mass spectroscopy, but it is not a proper name. And in advanced versions or the new textbooks, whatever have come to the market now, they are called as mass spectrometry. So it is called MS, that is mass spectrometry. As well as in the first module, we are concerned to study with introduction, principle, and some of the instrumentation techniques involved here. Before going into the actual topic, let us study some of the basic introduction or general introduction with respect to mass spectrometry. So this mass spectrometry is essentially an analytical technique which is used for the determination of molecular mass and structural information of the compound. As the name itself is indicating mass spectrometry, so this spectroscopic technique is highly useful to determine the molecular mass of the compound. Not only molecular mass you will get, based on the fragmentation mode that you will see in the next modules, you can arrive at the probable structure of the organic compounds. Unlike other spectroscopic techniques, in mass spectrometry, you need to use very, very small quantity of the samples of the order of nanoscale. Say, for example, if you use 1 mg in 1H NMR, maybe here you can use 0.01 mg, or even less than that you can use for the determination of the mass. So here very, very less quantity of the sample is used of the order of nanoscales. And here the main thing that involved in mass spectrometry is production and separation of ionized molecules. So whenever you have got a molecule, you have to subject it to ionization. After ionization, the product undergoes decomposition. You have to measure the relative abundances of the different ions produced in the mass spectrum. As I said earlier, this is not a true spectroscopic technique because there will be no absorption of characteristic radiation, and hence we say that it is not a true spectroscopic technique, but still we consider this as one of the spectroscopic techniques. And here in this case, when you subject the sample to mass, there will be no recovery of the sample, meaning to say that the sample undergoes decomposition, the fragmentation takes place in this mass spectrometry. As a result of that, we can call this as a destructive technique, wherein if you take a molecule, say A, B, C, and subject it to mass spectrometry, you will get A plus B plus C, so you won't be getting A, B, C. Whereas in 1H NMR, if you remember, you take the sample, you put it in the NMR tube, and you dissolve it in some solvent, you scan for NMR, and you take out the sample. By just removing or say shaking with excess of water, you will get back your sample. Whereas in this case, it is not possible to get back the sample, and hence it is called a destructive technique. Another important feature or characteristic feature of mass spectrometry is that this can be used as a chemical fingerprint. You know that each individual on this earth is different. That means every person has got different chemical fingerprint. Every person has got different thumb or fingerprint, whereas even in mass spectrometry, we follow the same rule in the sense that if you take different classes of organic compounds, each class of organic compound, it gives different types of fragmentation mode. So for example, if you take alkane, alkene and alkyne, in all the three you will see that the fragmentation mode will be entirely different. So it is for that reason, just by looking at the characteristic fragments that are produced in the mass spectrum, you will see that this molecule belongs to a particular class of organic compound, and hence mass spectrometry can be used as a chemical fingerprint to characterize the sample. Coming to basic principle, here instead of using any radiation, we use a beam of highly energetic electron, say roughly of 70 electron volts. So whatever you have got the sample, the prerequisite for the mass spectrometry is that the sample should be in the vapor phase. So you take the sample, vaporize it, and then bombard the molecule with very high beam of energetic electrons, say roughly 70 electron volts. When you bombard the molecule, it results in the formation of positively charged ions, and they are called molecular ions. Also, they are called as parent ions. So these molecular ions or parent ions are generally represented as M plus radical. So the additional energy which is available with the electrons, what it does is it results in the breakdown of the molecular ion or the parent ion into small fragments known as daughter ions. Here, there will be a loss of electron from the molecule that leads to a radical cation, and the entire process, whatever we have discussed here, that can be represented in the following equation. Here M is any molecule, say any sample of interest. You bombard the molecule with electrons of very high energy, that is 70 electron volt. So a molecule which is having electron, that one of the electrons it will be lost, and that's why we are represented as plus. When one electron is lost, another electron will be remaining. So this is called radical cation. There is a radical, there is a cation. This radical cation is also known as molecular ion. It is also called as parent ion. So we have already got excess energy in the form of electrons. So one E will be there. One electron is lost from the molecular, from the molecule. So that electron will add up to this electron and it becomes 2E. This is the general representation of the formation of molecular ion from a molecule in the mass spectrometry. So as I said, the energy possessing by the energy possessed by the electrons will be very, very high. So whatever the molecular ion is there, this will undergo further fragmentation to form what are known as daughter ions, or these are also called as fragment ions. So M plus radical is called as molecular ion or parent ion. The small m's, they are called as fragment ions or daughter ions. The fragment ions, it can be a radical, it can be a cation, or sometimes it can be a neutral molecule, and again there can be a radical cation. So different kinds of products, they are called secondary products, or they are called as daughter ions. These different daughter ions, they are separated by deflection in the presence of a variable magnetic field according to their mass, charge and velocity. Here, as far as mass spectrometry is concerned, you need to mainly concentrate on mass and charge of the ion found. So when they are deflected, they generate a current called as ionic current at the collector in proportion to the relative abundances, that I'm going to explain what is relative abundance short while from now. So for a given charge, velocity and deflecting force, the deflection will always be less for a heavy particle and the deflection will always be more for a light one. In the means to say that you take a big rock and look at the movement of the rock. When you take a big rock, the movement will be very, very difficult. When you take a small stone and throw, the small stone will go very fast, whereas the big rock cannot move very, very fast. In the same way, for the given charge, velocity and deflecting force, the deflection is very less for a heavy particle. That means if the mass of the product or the daughter ion formed is very, very heavy or more, the deflection will be less, and vice versa. That means if the mass of the daughter ion formed is very, very less, then the deflection will be very, very more. That means the velocity, or say the movement of the ions in the spectrometer, will be high for the lighter ones and it will be less for the heavier ones. As a result of that deflection, you will see that a number of beams containing ions with the same M by Z values are obtained. Here M by Z, M is the mass, Z is the charge. So M by Z is the mass to charge ratio, and different peaks will be obtained. These beams are made to strike against a photographic plate where not only they appear as separate lines, but the intensity of each peak is also recorded. This is a typical mass spectrum. This is some ester. You don't have to worry about the ester right now, but how a mass spectrum is obtained? It is obtained by the plot of relative abundance on y-axis and mass to charge ratio represented as m by z. Henceforth, we are not going to tell it as mass to charge ratio. Simply, we refer it to as m by z, and m by z will be plotted on x-axis. So, relative abundance or intensity on y-axis, m by z value on the x-axis. So, m by z value, you will see that there are number of beams. Each line in this mass spectrum is called as a peak. Here you won't be seeing a bell-shaped curve, rather you will see in the form of lines, and each line is called as a peak. Here you will see that whatever the peak has got the highest molecular weight in the mass spectrum, that is called as molecular ion or parent ion, represented by M plus radical. So this is a typical mass spectrum. When you do all the above, as I said earlier, you will get a mass spectrum, and this is a typical mass spectrum. You will see that number of lines will be obtained. So mass spectrum is the plot of relative abundance versus m by z value. In what way mass spectrometry differs from other spectroscopic techniques? So mass spectrometry, as I said earlier, it does not involve characteristic absorption of radiations, whereas it is observed in other spectroscopic techniques like UV, IR and NMR, where the sample absorbs the characteristic radio frequency energy, and hence they are called spectroscopic techniques. We call UV spectroscopy, IR spectroscopy, NMR spectroscopy, whereas in the case of mass, there will not be any absorption. That's why it is called mass spectrometry. That is the first basic difference between mass and other spectroscopic techniques. Whereas the second difference between them is that mass, as I said, it is a destructive technique, meaning that once the molecule is subjected to mass spectrometry, the molecule will be undergoing fragmentation to form different secondary products. They are called daughter ions. So that's why there will be an irreversible chemical change in mass spectrometry, whereas in other spectroscopic techniques you will see that there will be reversible physical changes. The change may be taking place, but it is only physical. That means you take a sample, you dissolve it in solvent, so there will be a change in the physical state. So once the analysis is done, you take out the sample, you evaporate the solvent off, and you will get back your sample. So this is reversible, just physical change. Physical change can be easily reversed, whereas chemical change cannot be easily reversed, and that's why they are called irreversible changes. These are the main two differences between mass spectrometry and other spectroscopic techniques that we have studied so far. So once we know something about mass spectrometry introduction and basic principle, now we have to move to the instrumentation, and the instrument which is used to record the mass spectrum is called the mass spectrometer. This is the diagram of the mass spectrometer. This is how it looks. It has got various components which we have to study one by one in detail. Before that, we will see what a mass spectrometer does. So as I said in the principle, it mainly generates positively charged ions from the sample of interest. So you take the sample, you hit that or bombard that with very high energetic electrons, that results in the formation of positive ions, and the ions formed are separated based on the m by z values. Once the m by z values are separated, based on m by z values are separated, it also records the relative abundance of each ion. What is the relative abundance? We will see here in the mass spectrum. This is the typical mass spectrum. There are several peaks, there are several lines. Among all these lines, there will be only one peak or sometimes two peaks which has got very high intensity, and the height of the peak refers to the relative abundance or intensity of the peak. Some of the peaks will be of very, very short in nature, some of medium, whereas one or two lines usually in the mass spectrum, they are of very high intensity, say 100%, and this is called the relative abundance. Coming back to instrumentation, the mass spectrometer, as I said, it does mainly the following three things. So in mass spectrometry, there are mainly two different types. One is single focusing mass spectrometer. The other one is double focusing mass spectrometer. Before the arrival of double focusing mass spectrometer, scientists or people were using only single focusing mass spectrometer, in the sense that they have only one analyzer in this, that is the magnetic analyzer. Using this instrument, scientists, they had lot of problems. This single focusing, they posed lot of demerits and disadvantages. As a result of that, they formed or they evolved another instrument called double focusing mass spectrometer. So single focusing mass spectrometer and double focusing mass spectrometer, essentially they will have more or less all the components one and the same except one item. Here there will be only one analyzer, that is magnetic analyzer, whereas in the case of double focusing instrument, you will see in a short while from now, there will be another additional analyzer called electric analyzer. Before to the magnetic field or magnetic analyzer, there will be another analyzer called electric analyzer. So any mass spectrometer essentially should have the following components. The first is the inlet system. Here is the insertion probe from where the sample of interest will be inserted into the system. Here the sample is vaporized. This is vaporization chamber. Here the ion source will be there. So here is the electron beam. That means from here you will generate the electrons, and these generated electrons will hit the molecule or sample of interest. It resulting in the formation of different ions. These ions will move to different slits. You can see here slits, horizontal line here, they are slits. So the main function of slits is to carry forward the ions in a particular path. So this is the ion beam. The ion beam will travel through a sufficient longer period of time and also for a longer period of length, and hence they have to be channelized using slits. And once the ions come out of the ionization chamber, this is the ionization chamber, they have to enter into the analyzer where they will be separated according to their mass to charge ratio. Here there will be only one analyzer, that is magnetic analyzer. Here you can see that ions that are too light bend too much. Here you can, here there are a lot of beams. When you come here, you will see that some of the items are going up, some of the ions are in the middle, some of the ions are coming down. That means they are also shown in different gradation, small, medium and large. The ions which are very, very smaller will bend very much and it will move very, very fast. The medium ions will travel somewhat late, whereas the heavy ions or heavy particles, they will not be moving very, very fast. So these are the ions that are too heavy, bend too little, and this is called the flight tube. We will see later what is that. Only ions of the right mass can enter the detector. So here this is the ion path length or the different ions path length. So those ions which have got the right mass, only they can enter into the detector cells, and the entire mass spectrum should be carried out in the evacuated chamber, or it should be connected to a vacuum pump. Here also there will be slits. You can see two horizontal lines. These are called slits, detector slits. Again, the function of this detector slits is to monitor the movement of the ions. Once the molecules comes to the detector, they will be collected and recorded in the form of a spectrum in the computer, and this is a typical mass spectrum. So these are the different components of the single focusing mass spectrometer. As I said, here the ions have to move in a bend curve for a sufficiently long period of time. So the ions will travel a considerable distance through the magnetic field to collector, and hence very low pressures are maintained by the use of diffusion pumps. So in order to create very low pressures, we need to use diffusion pumps in the mass spectrometer. As I said, mass spectrometer is usually operated in high vacuum. It is just to see that we will eliminate the undesirable collisions between the ions and the neutral molecules, as well as sometimes the collisions will take place between the ions themselves. So in order to eliminate all those undesirable collisions, we have to carry out the entire experiment in high vacuum. This high vacuum also, it prevents gas discharge from high voltages in some ion detectors. Not only that, it minimizes the noise, what is known as background, and also sometimes it minimizes the cross contamination between one sample to another sample. So because of all these advantages, the entire mass spectrum should be placed in a very high vacuum. So this is the typical schematic of a double focusing mass spectrometer. Essentially, almost all the components as discussed in single focusing, they hold good here also, except for the one component, that is here there are two analyzers. There is one magnetic analyzer. Before magnetic analyzer, there will be one electrostatic analyzer. So this is the analyzer part. We have to discuss all the components in detail. This is the inlet system. You can see that there will be a reservoir, and this is called the ampoule, and there is a sinter here from where the sample is inserted. The sample can be in the form of solid, liquid, and gas. We will see what sample has to be introduced in what way. Then once the sample is introduced into the inlet system, the sample will go, it will get vaporized here and then goes to the ionization chamber. You will see that the ionization is done by different techniques like electronic ionization, electron ionization, chemical ionization, field desorption. There are several techniques. We will come to the details of that later. So in the ionization chamber, you will see that there will be anode and cathode. That means the ionization is electrically conducted, and there will be different chambers in the ionization chamber, say A, B, and C. So these are all slits. So once the sample undergoes ionization, the different ions are produced and they will be present in the form of a beam, and the ionic beam will pass through the slits here. You can see number of slits present, and here is a curved, big curved tube. Through this curved tube, the entire ionic beam has to pass. First, the ion beam or different ions produced will pass through electrostatic analyzer. Here you can see that electrostatic analyzer is connected to positive and negative terminal. Once they come out of the electrostatic analyzer, there will be monitor slits. The monitor slit is just to see that the ions are moving in the right path. Once the sample, the ions come out of the electrostatic analyzer, again it has to go through monitor slit and come to magnetic analyzer. This is the analyzer part. After coming into the magnetic analyzer, here almost the molecules or the different ions produced in the system will have got deflected and separated. So based on the mass, charge, and deflection, once the different ions are formed, only the right mass can enter into the detector and collector part. So this is the detector and collector part. Once it is detected and collected, it will go to amplifier, and in turn it will be recorded into the computer in the form of a spectrum called mass spectrum. So essentially, mass spectrometer will have 5 different components: 1 inlet, 2 ionization chamber, 3 analyzer, 4 collector detector, 5 amplifier, and recorder. We have to study all the 5 components in detail now. We shall now study about all the 5 components in detail. The first one is sample inlet system. So this is how a sample inlet system will be. It is just a block diagram. Here the gas is introduced, and this is the place where we inject the liquid. If the sample is a liquid, if the sample is gas, so it will be in the container. We just transfer from one container to the inlet system, and if the sample is solid, it is just placed on the inlet tube directly by heating the probe tip. Once the sample comes here, there will be different controlling systems. So this control is to see that the samples are moving in a uniform speed inside the system. So these are called valves. Once the sample goes here, it will come to the oven. So here the vaporization takes place. As I said earlier, all the samples which are entering the mass spectrometer instrument, they have to be vaporized first. So this here it undergoes vaporization, and then from here it will go to the ion source where it will undergo ionization to produce different ions. So any sample for that matter, you cannot just insert into the mass spectrometer instrument. There are several prerequisites for the sample inlet system to be followed before using mass spectrometer instrument. The sample should be present in the vapor phase before ionization. So whatever the sample you have, whether solid, liquid, or gas, it has to be vaporized first and converted into the vapor phase. So the sample, if it vaporization means it is just heating. So if your sample is thermolabile, that means if it undergoes decomposition at the first step itself, then the sample cannot be used for mass spectrometer. So the sample, it should not undergo thermodecomposition or thermal decomposition during the vaporization process. The molecule should be intact. At the first instance itself, in the vaporization chamber, the sample should not be harmed. The fragmentation can take place only in the ionization chamber and not in the vaporization chamber. And another important prerequisite in the sample inlet system is that the pressure should be kept as low as possible inside the system. And these are the three prerequisites for any sample in the inlet system. So this is about the first component, sample inlet system. So here the organic compounds that have moderate vapor pressures up to 300 degrees Celsius, they can be subjected into mass spectrometry by placing that in an ampule connected via reservoir to the ionization chamber. The solids, as I said, can be directly inserted into the ionization chamber, and their volatilization is controlled by heating the probe tip. If it is gas, then it is transferred from one container to the reservoir, and if it is liquid, you can use the special syringes available for injecting the liquids into the inlet system. So whatever may be the sample physical state is, but you have to convert that into vapor phase. That is one of the prerequisites that we have discussed earlier. And the second component in mass spectrometer is that ionization. So there are different types of ionization techniques. We have to study one by one, and the first one is the electron ionization method. In general, we call it as EI, electron ionization, EI. So it is called as EI. This is one of the simplest methods and most widely used method for the ionization of molecules in the mass spectrometer. Here what we does is, so this is a molecule. This molecule, just consider it as a parent molecule, and there will be a very highly energetic electronic beam. So when the sample moves in the system, this electronic beam, it will hit the molecule and it produces ionized parent molecule. Along with that excess of electron, it will further fragment this parent ion into daughter ions. So here usually the volatilization is done in a separate chamber, and the pressure should be kept as low as possible, of the order of 10 raised to minus 4 to 10 raised to minus 5 torr, and then it is allowed to leak into the ion source. Here the ionization takes place by bombarding the sample with highly energetic electrons. So these electrons are generated by heating either tungsten or rhenium filament. Here on the, this is the ion source, and the opposite side of the ion source there will be a plate called as the electron trap. Here the electron trap is, it has got an electrical connection to the filament, and it is held at the positive potential with respect to the filament. Here both positive, negative and neutral charges containing ions are produced, but our main interest is to focus on positive ions only, whereas negative and the neutral molecules we have to, or ions, we just have to push it out of the system. How we can do that, we will see. The negatively charged electrons are drawn towards the trap. Here there will be a trap, and they travel across the ion chamber as well as the defined B by means of the small magnets called collimating magnets. And this is one of the instrument or unit used for electron ionization technique. Here the sample is passed from this end, there will be electronic beam. So once the sample is passing here, it will come in contact with the high energetic electronic beam, and the molecules or the sample of interest will undergo ionization in this system. So this is the system or unit used for EI, that is electron ionization method. So in this case, the normal process takes place. There will be a molecule or sample of interest. Then you heat that molecule with high energetic electrons. So the one of the electrons in the molecule will be released. So it becomes M plus radical. This M plus radical is called as molecular ion. Along with one electron, the one more electron will be coming from the molecule or the sample of interest, and hence it becomes 2e here. The accelerated electrons usually will have very high energy, produce positive ions, small amounts of negative ions, as well as neutral particles. But we have to mainly concentrate on the positive ions. So these positive ions are selectively pushed out by using electrodes with a small positive charge that is used as the filament. The negatively charged ions are usually abstracted, and they are neutralized by the pusher plates, because we are not dealing with the negative ions as well as the neutral particles, even which are pumped out of the system. Finally, whatever the positive ions we get, and they are accelerated by electrodes which are maintained at very high potential, and they are focused in the form of a beam, because they have to go to the detector where it is detected. Usually the time taken for the formation and ejection of ions, it is of the order of 10 raised to minus 8 seconds. That means within just a wink of the eye, the entire process takes place. Whatever we have studied or seen in the last two slides, everything takes place in just 10 raised to minus 8 seconds. That means the system is very, very fast with respect to EI method. The next one is the CI method, that is chemical ionization method, CI. As the name itself is indicating here, we have to make use of some kind of chemical substance, and the chemical substance is usually called as reagents. Usually methane, isobutane or ammonia are the usually used reagents in the CI system. They are introduced in the system into a very high pressure source and bombarded with electrons to get ions. So here, before bombarding the sample, first you have to bombard these chemical reagents. These chemical reagents will in turn react with your molecule and they produce ions. Here you can see here, first there will be a reagent gas. First this reagent gas, they have to be bombarded with the electrons and they produce the positive charged ions. Once these positive charged ions or you can say reagent ions are formed, then you subject the sample into the system. The sample will now react with the reagent ions and then may move towards the analyzer. So this is the electronic source. This electron source, what it does, it mainly hits, this is very highly energetic electron beam, it hits the molecule and converts the reagent gas into ions. So here two kinds of ions are produced, primary ions and secondary ions. The primary ions produced undergo ion molecule collision to form a stable population of secondary reagent ions, and these processes are shown in the following equations. So here we take methane as the representative example. We take methane and bombard it with high energetic electrons. So one of the electrons from the methane is released to become 2e, one electron coming from another, one more electron coming from methane, it becomes 2e here. Because it lost one electron, there will be a radical and there will be a shortage of electron. That's why we represent it by plus, and this is a radical cation. Now this radical cation so formed, it will collide with another neutral species, that is neutral molecule, another methane molecule. Here this one methane acts as proton donor and another acts as proton acceptor. Here methane acts as proton donor and this acts as proton acceptor because it has got one electron short. That's why this one electron will be neutralized by donating one proton from this molecule to this molecule. So if one proton is donated to this becomes CH5 plus and this becomes CH3 radical. This CH5 plus is called as methanium ion. This is called secondary reagent ion. This is the primary reagent ion. This is called secondary reagent ion. So whatever the CH3 cation is formed, that will further react with one more molecule of methane and it forms ethyl cation C2H5 plus and one H2 gas is released. Now methanium ion, it will be treated with base. Now this green color plus indicates methanium ion, blue color indicates our sample or molecule. This molecule is M, that is substrate here. So what happens? Here CH5 plus is highly unstable. It passes one H to the substrate. It becomes MH plus and CH4. The stable methane is liberated again. If the sample of interest or molecule is acidic enough, then what happens is one hydrogen is lost from the molecule. In this case, the regular molecule or sample of interest, it will gain one hydrogen. If the molecule is acidic enough, then it loses one hydrogen. So COOH, H will be usually eliminated to form M-1 and here CH4 and one molecule of hydrogen is liberated. So these are the reactions that takes place when we use methane as the chemical substance for the generation of ions in the chemical ionization method. So here, whatever the MH plus produced, that is called quasi-molecular ion. So MH plus ion is the ion which has got a mass value 1 AMU greater than that of the molecular ion. What is AMU? Atomic mass unit. M is just molecule. For that molecule, one hydrogen has come. So hydrogen has got atomic mass unit of 1, because atomic number and atomic mass of hydrogen is 1, and then that's why it is called M plus 1, or simply we can call it as MH plus, and that MH plus is called quasi-molecular ion. This quasi-molecular ion, it can undergo fragmentation or loss of hydrogen to give prominent M minus 1 peak. So what happens? This MH plus, it loses one hydrogen. So one hydrogen is lost, M1 hydrogen is lost, that is minus 1, it becomes M minus 1, and a molecule of hydrogen is liberated. Here, the M plus ions usually undergo less fragmentation because they have got very, very less energy. So MH plus will be the prominent peak in the mass spectrum. So whatever the mass spectrum we get for CI, it will be very different from the conventional one, that is EI. So whatever the peaks you get in EI, that will give peaks only because of molecular ion, whereas in chemical ionization method, you will get different kinds of peaks, maybe MH plus or M minus 1, either addition of hydrogen or deletion of one hydrogen from the molecular weight of the sample. So in that way, the CI spectrum will be somewhat different from the regularly used EI spectrum. There are several advantages of CI over EI. Let us see one by one what are the advantages. Here in CI, more abundant peaks related to the molecular ion region, that is either M plus 1 or M minus 1 are obtained and nothing else. So it will be very easy for us to interpret what is the molecular weight of the sample. Whereas in EI, you may get number of different peaks of equal intensity that leads to very difficult interpretation. Whereas in CI, such case is not there because you get either M plus 1 or M minus 1. So whatever the molecular weight you get, it should be either with plus 1 or minus 1, and that will be of very, very high relative abundance. That means the more abundant peaks are found. And in using chemical ionization method, the fragmentation mode will be very, very simpler. That means you get either M plus 1 or M minus 1, that's all. That will be the prominent peak. Whereas in EI, that is not the case. You will get number of peaks that leads to difficulty in the interpretation. And moreover, when you use CI method, you can apply the GCMS. GCMS is gas chromatography mass spectrometry. So you can do purification or separation. GC is a separation technique. You can do separation as well as you can find out the molecular weight of the ion or any product that is separated. So because in GCMS, so in GC you can see that gas chromatography, the name itself is indicating we have to make use of some kind of gas. So this methane, it can be used as both carrier gas as well as the chemical substance. So chemical ionization means we have to make use of some kind of chemical substance, use methane, and the same methane can be used as carrier gas in the gas chromatography. So it is tandem gas chromatography mass spectrometry. So once you use, you can, it is cost effective because methane can be used both as carrier gas as well as the chemical reagent used for the ionization purpose. So these are the different, several advantages of chemical ionization over electron ionization. The third technique that we have got is called field desorption or desorption ionization technique. Field refers to electrical field. Here, instead of absorption, the desorption takes place. Desorption is just movement. Absorption is getting itself inside. Here, there is no absorption, rather we have got desorption. So once the ions are generated here, they are easily swept out of the system by means of some electrical field, and hence it is called as field desorption. In short, we can call it as FD. FD. It is also called by another ionization technique called desorption ionization technique. So it is DI. The main principle here is the desorption. It is opposite of absorption. So in EI and CI, when you do, you cannot use non-volatile samples or the samples having very high molecular weight. So EI and CI, you will see that there will be more volatility because you are going to subject the molecules into vaporization chamber before they enter into the ionization chamber, and hence if the sample is non-volatile, that means even if you try to volatilize, the sample will not undergo volatilization. Such samples can be easily subjected to FD or DI, wherein the molecule can undergo easily ionization, and such compounds can be ionized by DI wherein the sample is directly placed onto the anode. So as I said, in the field desorption, we make use of electrical field here. So this is the probe carrying emitter. Here we place the sample, and this is the ion source, the yellow color one. So once the ions are generated, here this is the ion emitter. From this end, the ions will be coming out, and you can see that there is counter electrode. There will be one anode and there will be one cathode, and there will be focusing plate here in order to see that the ions are moving in the straight path. And once the sample or the ions come out of the ionization source, it will be moving to the analyzer. Here, the intense electric field brings about ionization and desorption. Compounds with very high molecular weight, for example, peptides, proteins, carbohydrates, alkaloids, steroids, etc., they are subjected to field desorption or desorption ionization technique because they have got very high molecular weight, say roughly up to about 5,000 kilodaltons. There are mainly two methods coming under this field desorption. They are fast atom bombardment, in short we call it as FAB. Another one is matrix assisted laser desorption ionization, in short we call it as MALDI. We will discuss both these now. The first technique under desorption ionization is fast atom bombardment. So the name itself is giving you a clue here, FAB, fast atom. So there should be an atom. The atom should be having very fast movement. Using that fast moving atoms, you have to bombard the sample. So that is the basic principle of FAB. So this is the unit which is used for the fast atom bombardment. Here we mainly use some rare gases like xenon or argon gases, and we bombard the gases with electron first and they produce atoms. These fast moving atoms are used for the bombarding with the sample here. So this is the fast particle beams, and they come to the, when they hit or bombard the samples, they produce secondary ions. These secondary ions will be moving into the mass spectrometer, and the inlet is here. So this is the unit used for FAB. Here, FAB is used for mainly polar compounds, say peptides. Before subjecting the sample into the inlet system, we have to mix the sample with usually a matrix, that is usually glycerol, and then bombarded with a beam of fast moving neutral atoms to achieve ionization. As I said, rare gases like xenon or argon are used here for bombarding purposes. So atoms of the gas are first ionized to get very high kinetic energy and then pass through the electric field. So whatever you do, here you have to generate the ions, you have to generate the atoms. The atoms generated should have very, very high kinetic energy, because fast atom bombardment, fast refers to movement, movement refers to kinetic energy. So whatever the atoms you produce, those atoms should have very high kinetic energy because they have to move very, very fast. So once you produce the highly kinetic energetic atoms, then they will undergo acceleration. The fast moving ions enter into the chamber containing further gas atoms, and here this is the xenon. Xenon, first I have already heated this with electrons to form xenon radical cation, and this will be having very, very fast movement. And whereas this xenon is in thermal condition, one is fast and another one is thermal. Once the acceleration is done, there will be exchange between these two. Look at here, the plus radical will be shifting here and the normal neutral will be shifting here. So xenon fast will become xenon, sorry, there is a mistake here. Xenon fast will become xenon thermal, and xenon thermal will become xenon fast here. So collision of ions and atoms leads to charge exchange. So this is what is represented here. This is the probe tip on which the sample is spotted along with the matrix. Here the matrix usually is glycerol, and then it is bombarded with very fast moving particles. Here green represent analyte ions and blue represent matrix ions. Here when the atoms are bombarded with very fast, when the sample is bombarded with very fast moving atoms, the ions get desorbed to produce secondary ion beam, and then in turn they will go to the extraction grid. From there it will go to the focusing lens, and then it will go to the mass analyzer. So mass analyzer, it essentially consists of both electric analyzer as well as magnetic analyzer, and then it will go to the detector. So the fast atoms so formed, it retains the original kinetic energy of the fast ions and they proceed towards the analyzer. So the remaining ions with thermal energies can be easily removed by a deflector plate with a negative potential. So whatever the remaining ions are there with just thermal energies, we want the atoms with only fast kinetic energy. The atoms which have got just thermal energy, they have to be removed by means of a deflector plate which is connected to a negative potential. So when the sample is bombarded with fast atoms, both positive and negative ions are produced. And if the plate on which the sample is placed at a suitable potential with respect to the ion exit plate, either the positive or negative ions can be directed towards the analyzer. That is what is depicted in this schematic representation. So here both positive as well as negative ions are produced and they are subjected to the analyzer where it gets separated based on the mass, charge and velocity. This is about fast atom bombardment. And there are several advantages in connection with the FAB. So FAB can be used for the ionization of very high molecular weight samples, whereas this is not seen in EI or CI. They are for the very low molecular weight samples. But what about high molecular weight samples? What we have to do? We can subject it to easily FAB. That is one of the desorption ionization techniques. Even the mass spectra of these salts can be recorded using FAB. Moreover, when you use FAB, you get relatively abundant M plus or MH plus. Either you get molecular ion or quasi-molecular ion, and the rest of the peaks will be very, very negligible, and hence the interpretation becomes very, very easy when FAB is used. In when we spoke about a lot of advantages, there are a lot of disadvantages also associated with FAB. We'll see here the spectra will be quite complicated because we are going to use matrix. Remember that we use glycerol. We first take the sample, we mix it with glycerol, and then we keep it on the probe tip. So here the matrix also undergo ionization. Because of that, eventually you will see number of peaks in the mass spectrum coming out of the matrix that leads to difficulty in interpretation. Here, when you take the sample mixed with matrix, when you subject the fast moving atom bombardment to the sample, here the bombardment will be taking place only on the surface, not inside the molecule. That is, bulk of the molecule is not undergoing ionization. That means this FAB cannot be used for quantitative measurement of the sample, and this is roughly for the qualitative measurement. So here FAB, it requires time in minutes and rather than seconds, whereas you saw that in EI or CI the entire process takes place in few seconds, that is 10 raised to minus 8 to 10 raised to minus 10 seconds, whereas FAB requires time in minutes. So these are some of the three disadvantages, but overlooking or bypassing the disadvantages, we have to mainly concentrate on advantages, because when we have the large molecular weight samples which cannot be subjected to EI or CI, where we should go in such instances, we can easily go for the DI, that is desorption ionization techniques, and FAB is one of that. The second method is MALDI, and it is expanded as matrix assisted laser desorption ionization. This is one of the desorption ionization techniques. Here the name itself is telling we have to make use of a matrix and we have to make use of a laser. So when we use laser, we will not be using any kind of electronic, high energetic electronic beam. That's why we say that MALDI is a soft ionization technique. What we do here, this is the matrix. In the matrix, we mix the sample. We will see what that matrix is now. So first take the matrix, mix the sample and heat with the laser. It is just a light of particular wavelength, lambda max, and the molecule undergoes ionization and they will move towards the analyzer. Mainly in MALDI, we make use of time of flight analyzer that we will study in the next module. So here, based on the velocity, different ions are separated and they are detected and recorded in the spectrum. So usually this MALDI is subjected to thermolabile molecules. What is thermolabile? If the molecules are very, very sensitive to temperatures, then such molecules can be easily subjected to MALDI in order to know the exact mass of the molecule. And it is also applicable for non-volatile organic compounds and also very high molecular weight compounds like proteins, peptides, some complexes, etc., they can be subjected to MALDI, and the sample will not be harmed because we won't use very high energetic electrons. Rather, the sample is bombarded with a nitrogen laser of lambda max 337 nanometers. So it is not very highly energetic radiation. That's why it is a soft ionization technique. And this nitrogen laser, it causes ionization of the sample. Here the sample before ionization or before nitrogen beam bombardment, we have to pre-mix it with highly absorbing matrix. Usually used matrix are nicotinic acid or synapinic acid. They are the matrix. Here, one important thing that you should maintain or understand here is sample matrix ratio should be as less as possible. The concentration you need to keep very, very less, because in mass, we need to use very, very tiny amount of the sample of the order of nanoscales, not more than that. If you give more sample, the different ionization channels which will be blocked, and that blocking leads to harm to the instrument. So here the matrix, it transfer first the laser energy, it will hit the matrix. So the matrix energy transforms the laser energy into excitation energy, and that leads to the sputtering of samples from the surface of the mixture. Usually whenever we use MALDI, we make use of time of flight analyzer, and this analyzer, the main function is to separate the ions according to M by Z values. There are several advantages of MALDI over other ionization techniques. So it is a soft ionization technique, as I said, because we are going to use wavelength of light just 337 nanometers. So it is not a hard ionization technique unlike EI or CI. And here the spectra is very, very easy to interpret, because only singly charged molecular ions are produced here. Because you will see that you will usually get MH, that is M+1 or MS, quasi-molecular ions are usually produced. So this is the process of MALDI. This is the MALDI plate. You will see number of circles here, both on vertical as well as horizontal positions. So once you take the MALDI, you clean it with some solvent, usually ethanol, and then you spot the sample. So before spotting the sample, you need to mix the sample with the matrix. Usually water is used for mixing, because we use highly polar compound, say for example peptides. So once the sample is mixed with the matrix and they are spotted on each circle here, then it is subjected to drying, air drying, just normal drying. Once the samples are dried, you will see that the dried samples are spotted on the MALDI plate, and then this MALDI plate is kept for ionization using nitrogen beam of lambda max 337 nanometer. So this is the process of MALDI. Now I'm going to show you a video, and in the next module we will learn about different analyzer. So we have first introduced the sample into the inlet system, and then we have ionized. The second component is ionization chamber, and in ionization chamber or ionization we use different techniques: EI, CI, DI. Under DI we have got Fab and MALDI. Now we will go to watch a video, and then we will meet you in the next class. Thank you very much.
Mass spectrometry allows chemists to weigh atoms and molecules not directly on a balance, but by measuring how ions formed from them are accelerated and deflected by electric and sometimes magnetic fields. There are many types of mass spectrometer, but they all work on this basic principle. This instrument is called a magnetic sector instrument. The sample is introduced here, and the positive ions are formed here by bombardment of the sample with a beam of electrons. The ions are then accelerated by an electric field and then deflected in a curve by a further electric field. They then bend through a magnetic field and are further deflected by another electric field here. The ions then enter a detector here. By varying the electric and magnetic fields, ions of different mass can be made to enter the detector. These pumps keep the interior of the instrument under a high vacuum. This is to allow the ions, which are moving at speeds of many kilometers per second, a free path without collisions with air molecules. As the ions are formed from molecules of the sample, they may fall apart or fragment. The ion of largest mass is often the parent or molecular ion, an ionized molecule that is not fragmented. Other peaks of smaller mass may represent charged fragments of this ion. The masses of these fragments may give clues as to the structure of the original molecule. Liquid samples are placed in the tiny sample tube as shown. Here, we're running the mass spectrum of limonene, an alkene which can be obtained from the peel of citrus fruits. Only a little is required. Mass spectrometry can detect down to as few as 10 to the minus 12 moles. Volatile samples can be run neat. Less volatile ones are dissolved in a solvent such as dichloromethane, which then evaporates. The sample tube is placed in this probe, which is then inserted into the instrument via an airlock, so that the vacuum in the instrument is maintained. Volatile samples will vaporize at the low pressure inside the instrument, but the probe can be heated to vaporize less volatile ones. The electrons stream out from a heated cathode towards an anode, which is held at a potential of around plus 70 volts relative to the cathode. This is the ionization chamber where the positive ions are formed. These are formed when high-energy electrons strike the sample molecules. You can think of this as the electron beam knocking out an electron from the sample molecule. The sample fits here, and ions pass out through this slit. The heater itself is here. The electrons are accelerating in this direction, and the ions stream in this direction through the slit. The positive ion beam passes between two charged curved plates, which deflect it in a curve so that it enters the area here, where an electromagnet produces a vertical magnetic field. This further deflects the beam in an arc of a circle. On emerging from the magnetic field, the beam is deflected again by another set of charged plates, which direct it into the detector. The amount of deflection by the magnetic field depends on the mass of the ion, strictly its mass to charge ratio, but the vast majority of ions have only a single charge. The deflection also depends on the strength of the field. Heavier ions will not be deflected sufficiently in the magnetic field to reach the detector. Lighter ions will be deflected too much. During a run, the magnetic field is gradually increased so that ions of successively greater mass enter the detector. The mass spectrum of limonene looks like this. Each vertical line, called a peak, represents a different ion, and its mass in relative atomic mass units is shown on the horizontal axis. The height of a peak represents the abundance of that ion. The peak at 136 units represents the parent ion, the whole molecule that has lost an electron. The peak at mass 121 units, 136 minus 15, is the parent ion from which one of the CH3 groups, relative molecular mass 15, has broken off in the ionization chamber. And the peak at mass 107, 121 minus 14, could be formed by further loss of a CH2 group. Other peaks are caused by more complex breakdowns and rearrangements. Simple mass spectra show the masses of ions to the nearest whole number, which is fine for many purposes. However, this instrument can display masses to 3 decimal places of an atomic mass unit. This is called a high-resolution spectrum. It enables us to distinguish between different molecular formulae which have the same relative molecular mass to the nearest whole number. Here we see that the relative molecular mass of limonene is 136.125. This means that we can distinguish C10H16 from, say, C9H12O, which would have a relative molecular mass of 136.194 to 3 decimal places. Many mass spectrometers are of desktop size. This one takes in samples from a gas chromatography instrument. As each component comes off the gas chromatography column, it is fed directly into the mass spectrometer. The combined technique is called gas chromatography mass spectrometry, or GCMS. This is the column from the gas chromatograph. This particular mass spectrometer does not use magnetic deflection of the ions. It uses a complex electric field. However, the principle of forming ions from the sample and separating them according to mass underlies all types of mass spectrometer. This is the gas chromatogram of an impure extract of orange zest. The large peak is limonene, and the others represent impurities. Clicking on the peak shows the mass spectrum of limonene.